Hi everyone, welcome to this video on the use of trig identities for integration. These questions are going to assume that you have worked through the trigonometry topic already, so you should be fairly familiar with the rules that are going to be used here. However, if you're not, you can always refer back to the textbook and in particular have a look at the revision part at the end of the chapter. That will give you all of the rules that you're going to need in this exercise. This should be a relatively short video. Just going to work through these 4 examples on screen at the moment, so we'll see how we go with them. Now the first one, the integral of tan squared x. It's not immediately obvious, we don't know that one, but using the Pythagorean identity we can rewrite it as the integral of sec squared x minus 1 dx. And that is something we know because we know that when we differentiate tan x we get sec squared x, so when we anti-differentiate sec squared x, that's just going to become tan x. When we anti-differentiate the minus 1, it becomes minus x, and then we end up with a plus c. So that's the first one. The second one is the antiderivative of cos squared x. We have a couple of options for cos squared x which come from 2 different rules. So the first rule would be the Pythagorean identity, which would give cos squared x equals 1 minus sine squared x, which isn't really all that helpful because we don't really have anything that's nice for sine squared x at the moment either. So let's sort of steer away from that one. The alternative would be for the double angle formula, which tells us that cos 2x is equal to 2 cos squared x minus 1. And I think this is going to be a much better option because we could rearrange this equation here to get cos squared x by itself. So we add 1 to both sides and then divide by 2, we'll get cos squared x equals cos 2x plus 1, and then that's all over 2. So this is a much better option because we can anti-differentiate cos 2x on 2. So I'm going to make that substitution now into the rule here. So we have the integral of, and instead of cos squared x, I'm just going to write it as cos of 2x on 2. I might even just put half out the front, and then plus 1 on 2 dx. And so then I can just work my way through this. So anti-differentiating half of cos 2x. When we anti-differentiate cos, it becomes sine. So that's going to be a quarter of sine 2x. And then plus x on 2. And always remember the plus c. Rightio. So on to the third example. And we have a pretty horrible looking expression there. What I'm noticing is that we have a sine 4x and a cos 4x, which this comes back to the double angle formula for sine, which says sine of 2 theta equals 2 sine theta cos theta. And so what we know then is that sine of 8x must be 2 sine of 4x cos of 4x. So the other problem here is that I have a 3 in front of it, which, well, I really want that to be a 2. So what I'm going to do is I'm going to take the integral here, just bring it down here, so that's going to be equal to, I'm just going to write integral of 2 sine 4x cos 4x dx. And the thing is, I've changed that 3, well, I've really taken the 3 out the front. And because I've just multiplied by 2 there to make it so it's a little bit nicer to fit with the problem, I need to also divide by 2 so that I'm maintaining the same expression or equation. So now I've got something I can work with, and so I can replace the 2 sine 4x cos 4x just with sine 8x. So that is the 3 halves of the integral of sine 8x dx. which I can now anti-differentiate quite nicely because sine just becomes negative cos, and so I get negative 3/16. The 8 goes into the denominator with the 2, and then cos of 8x plus c. So again, quite nice. The last example is a little bit nastier. Sine cubed x cos squared x dx. So firstly what I'm going to do is I'm going to break this into sine x multiplied by sine squared x multiplied by cos squared x. Oops, don't need that, it's just dx. Now what I'm going to do next, basically I'm thinking I could probably put all this in terms of cos and make it fairly nice. So write as the integral of sine x, and then sine squared x can be written as 1 minus cos squared x from the Pythagorean identity, and I've still got another cos squared x dx. So at this stage I'm going to use a substitution. I'm going to let u equal cos x, which means that du dx should be, now differentiating cos gives negative sine, and so I can substitute these into the rule now. Now that instead of that sine x just there, I want it to actually be negative sine x, so I can write it as du dx. So I'm just going to write that as negative sine x, but because I've introduced a negative, I need to put another negative out the front to counter that. Then, well, I'll just leave this as it is for the moment. So 1 minus cos squared x times cos squared x dx. And now I know that's going to be negative integral of, this first part is just du dx here. So I'm going to have 1 minus u squared. Oh, just bear with me for a second. Okay, and then we've also got u squared outside the brackets there, and I have the du dx, which was the negative sine x, so I've still got a dx there. So the dx's cancel each other out. Left with negative integral of u squared minus u to the 4 du, which that should be fairly nice, and I might even just multiply the negative back through to make it a little bit easier. So that's just the integral of u to the 4 minus u squared du, which gives us u to the 5 on 5 minus u squared on, u cubed on 3, and then plus c. And so making the substitution again, u was just cos x, and so we end up with cos to the 5x on 5 minus cos cubed x on 3 plus c. Anyway, I think that's all there is for that video, so we'll leave it there and see you next time.